Okay, everyone, we are back at section 3.4, talking about quite a broad topic actually, which is a Bayesian model comparison. So how to choose between models of different complexity in the Bayesian way, and we'll see that it's kind of taken care of naturally for us. And the usefulness of this is it can be used to avoid, as we'll discuss, having to split your data into kind of a training set and a test set and a validation set, because by just using the laws of probability, you can essentially automatically avoid things like overfitting, which is the reason why we do all that stuff in the first place. In practice, it will turn out, and he'll kind of mention this at the end as well, that we will still end up having to do, for various reasons, we'll still end up having to do the cross-validation stuff anyway, but I think it's still useful to understand the Bayesian model comparison approach, because it kind of tells you where the overfitting is coming from, and it kind of gives you a good theoretical understanding of what's really going on when you're comparing simpler and more complex models. So I think it kind of gives a very natural and very very kind of simple understanding of how to deal with model complexity, which you can always try in practice, and you should try. And even if for whatever practical reasons you can't actually use it, it's kind of just nice to know about and kind of have in the background. So let's get into it. Okay, so it says in chapter 1 we highlighted the problem of overfitting, as well as the use of cross-validation as a technique for setting the values of regularization parameters, or for choosing between alternative models. So I think you had a really nice example there where where data was coming from, I think it was a sinusoid, and we were fitting different order polynomials to it. And these are also linear regression, because even though we were using x squared, x cubed, x fourth, and so on, those were features in our model, and our model was linear in the weightings that we were applying to those features. And we found that, for example, when we had, I think, 9 or 10 data points, the 9th order polynomial fit the training data very well. But then obviously on unseen data, which is what we really care about, it did really poorly. And so, back then we talked about, well, what you want to do is maybe put in some kind of regularization, try to keep your weights from getting very large, because that's what was happening when we were overfitting to the data. But we'll see that actually, there is a kind of a more natural and kind of almost like a proper way of dealing with these things, which doesn't really require like bringing in regularization and things like that. Or to put another way, there's kind of a natural regularization that happens of complex models, so you don't have to actually kind of bring it in artificially yourself. Okay, but let's just see what happens. So this section actually is also all about kind of intuition. So there aren't any kind of very solid calculations, but there are some they're very useful approximations that we're going to use. That'll kind of give you a big picture of kind of what's going on. The calculations will come in the next section, section 3.5. Okay, so as you said, in our discussion will be very general, and then in section 3.5 we shall see how these ideas can be applied to the determination of regularization parameters in linear regression. Okay, so as we shall see, the overfitting associated with maximum likelihood can be avoided by marginalizing over the model parameters instead of making point estimates of their values. So what we're going to do is we're not just going to say, well, report the performance of the best fitting set of parameters, but actually weight all of the performance of all of the parameters over our entire parameter space. And it will turn out that when you have more parameters, yes, typically your best fit will be amazing compared to the simpler models, but because you have lots of terrible fits as well, you get a natural regularization. That's the basic idea. Spreading you have to spread the fits over a larger set of parameters, and the very best ones are often not enough to make up for the many more terrible ones that you have. So that's how your complex models get penalized naturally. So let's see how this is going to happen. Okay, so models can then be compared directly on training data without the need for a validation set. So we don't have to throw away or keep data away from training. All the available data is to be used for training and avoids the multiple training runs for each model associated with cross-validation. And it also allows multiple complexity parameters to be determined simultaneously as part of the training process. So let's just highlight that as well. Right. And we're going to see, for example, in chapter 7, there's something called the relevance vector machine, which has a complexity parameter for every training data point, but let's talk about that then. Okay, so the Bayesian view of model comparison simply involves the use of probabilities to represent uncertainty in the choice of models, along with the consistent application of the sum and product rule of probability. So this is what's kind of really, as you know, as he emphasizes, and I'd like to emphasize as well, this is what's so useful and so clean about the Bayesian approach, right? It just tells you what to do from very simple, just sum and product rule of probability. Like that's all you really need. Obviously, there's a lot of the devil's in the details, so you actually be computing the integrals, and all these things can often be very difficult. We have to make approximations, but everything is just fundamentally is coming from a very simple and very consistent, logically coherent place. We don't have to do things arbitrarily, and when we do things, when we start having to make approximations, we can kind of be very explicit about those. And we'll see here that those same very simple ideas allow us to deal with model complexity, which I think is pretty awesome. Okay, so suppose we wish to compare a set of L models. So for example, these would be like the linear model, the quadratic model, and so on, for a given data set. So here model refers to probability distribution over the observed data. In the case of the polynomial curve fitting problem, the distribution is defined over the set of target values, while the set of input values is assumed to be known. So in that setting, we have some targets, and each of those models is going to give you some distribution on what it thinks the targets will be. So for the linear model, we'll think everything falls on the line. The quadratic model will try to make parabolas, etc. Other types of model define a joint distribution over x and t. It's not really important for now. We shall suppose that the data is generated from one of these models, but we are uncertain which one. So our uncertainty is expressed through a prior probability distribution P of mi. So this is how likely you think each of the models are. And I think oftentimes we can just set this to be the same for all of them. So actually we assume all the models are equally likely, because we won't have to explicitly penalize the models here. The complex models are going to get penalized naturally. So given a training data set, we then wish to evaluate the posterior distribution. So picking what is the posterior of my particular model given the data. And as usual, it's proportional to the prior times the likelihood of that model. The prior allows us to express a preference for different models, and let us simply assume that all models are given equal probability. The interesting term is then the model evidence. So again, there's a bit of terminology you have to remember, but you don't actually, you can always look up a terminology. The key is this expression, which expresses the preference shown by the data for the different models, and we shall examine this term in more details shortly. The model evidence is something also called a marginal likelihood. So it's kind of the likelihood, or can be viewed as a likelihood function over the space of models. So there we go, in which the parameters have been marginalized out. And the ratio of model evidences, so the posterior on the data given one model to another model, is a Bayes factor. And this will come up towards the end of the section, actually, in a really cool way. But in general, you're going to want to favor the model for which the data is more likely. So that will mean the one that has the highest, I guess it kind of wins out in all these Bayes factor computations. Okay, so once we know the posterior distribution over models, the predictive distribution is given, again, from the sum and product rules, right? So remember that we, often, and I guess in this case, actually, I was going to say often what we care about is prediction, but actually very frequently we do care about which model is correct. Like we want to say, well, is this interaction linear or quadratic? So it's not like sometimes with the parameters where we don't actually care about the parameter, we just care about the prediction. Here we actually do care frequently when we're doing model selection, like which is the right model. But nevertheless, okay, so here let's say we're just going to predict. We want to predict a new value, so given new inputs. And our data, well, again, sum and product rules. We just take the prediction for a given model, and then we weight it by the model. It's not quite the model evidence. Whatever the posterior, the posterior on the model, or the probability of the model given the data. So the main thing here is that we're weighting the prediction of each model by the probability of that model given the data. Okay, so this is an example of a mixture distribution in which the overall predictive distribution is obtained by averaging the predictive distributions of individual models, so this thing again, weighted by the posterior probabilities of those models. So again, if we have like two models that are a posteriori equally likely, and one predicts a narrow distribution around t equals a, and while the other predicts a narrow distribution around t equals b, the overall predictive distribution will be a bimodal distribution with modes at t equals a and t equals b, not a single mode at the average. So you're kind of getting a mixture of the two. So this is pretty cool, and what we often kind of encounter is actually taking the most probable model, so taking kind of maybe the map estimate over the models, and this is known as model selection. So instead of averaging your models, you just want to know, okay, which model fits my data best, so you pick the most probable one. That's model selection. For a model governed by a set of parameters W, the model evidence is given from the sum and product rules of probability by this. So this is actually pretty cool. Let me erase some of this so you can actually see it more clearly. Okay. And so this is actually quite cool, right? Because so what are we looking at? We're looking at the probability of the data given a model. And so, well, the model has these parameters W, so we're integrating where we're computing the probability data given one set of parameters, and then we're averaging that over the over the entire space of parameters. So this is kind of the key expression here, that the data might be under your particular model. Imagine like your model is the ninth order polynomial, right? The data is then going to be like, this probability is going to actually be really quite high, right? Because you'll have weights that are going to fit your 9 data points perfectly, right? So it's going to give you like an amazing value. But unfortunately, you can't just use that weight. You actually have to average over all the other possibilities that your ninth order polynomial allows you, and most of those are going to predict your data, going to fit your data pretty poorly, right? They're going to just give you crazy ninth order polynomials that are like completely different to the data that you have. And so this is really, really important. Essentially, this is kind of the key expression, probably the key expression of this section. So it's not just about fitting the data for a given model, but then averaging over the space of parameters of your model. And he also kind of gives it kind of you can think about it from a sampling perspective. So the marginal likelihood can be viewed as the probability of generating data set D from a model whose parameters are sampled at random from the prior. So what we do is we're going to take a W, sample it from this prior, and then see how likely was our data given those parameters. So the probability of generating data from a model whose parameters are sampled at random from the prior. And so imagine in that ninth order polynomial case, it's pretty unlikely that you're going to get a good fit to your data from random samples of those 10 parameters, right? Most of them are going to be completely off, and that's kind of where the regularization is coming in. It's also interesting to note that the evidence is precisely the normalizing term that appears in the denominator in Bayes' theorem when evaluating the posterior distribution over parameters, because so he's just saying that shows up there. I'm not sure why he's emphasizing that. So yeah, if you guys know, please let me know in the comments. But yeah, indeed, if you're kind of trying to get the posterior on the weights, well then the term that's going to show up on the denominator is going to be the integral of this with respect to W, which is precisely that term there. Okay, I guess the marginal likelihood. In this next little paragraph, he's going to use kind of a simple example to give us, and kind of make some simple approximations to give us intuition about how this important integral works and kind of how the regularization comes in. So let's see what he says. Okay, so we can obtain some insights into the model evidence by making a simple approximation to the integral over parameters. Consider first the case of a model having a single parameter W, so like the linear case with no offset, etc. The posterior distribution over parameters is proportional to P of data given to the likelihood of the parameters times the prior. So that was just the Bayes rule, and that's again this thing, this expression here, but just dropping the MIs because we're going to omit the dependence on the models to keep the notation uncluttered. So now if we assume that the posterior distribution is sharply peaked around the most probable value, W map, with width, that thing, delta width posterior, then we can approximate the integral by the value of the integrand at its maximum times the width of the peak, right? So that's just a simple idea that, if the integral kind of looks like this, well, we can just say, well, it just looks like, replace it by just a rectangle. Okay, so now, but what is that peak? Well, that peak is going to be roughly equal to the value of the likelihood at the map estimate, and P of W. So, but what about P of W? Well, if we further assume the prior is flat with delta W prior, so that P of W equals 1 over delta W prior, then we have this approximation. So let's just make sure kind of we get where that comes from. I think it's a simple idea. So we're going to say that this integrand is going to be sharply peaked. And so we're going to say that it's going to be peaked around we're going to assume it's going to be peaked around its most at the map value for W. So we're going to say that this expression here is kind of integral, whatever it is, W P of dW times PW. So the posterior distribution will have a peak. So it's going to have a peak at W map. So this is going to be W map, right? Because this is PW given data, which is proportional to P, Okay, so this is kind of what we have in here. Okay, and now we're going to approximate it by its value times kind of this width. So that width is delta W posterior. And what is the height? Well, the height is going to be P of W, so we just plug in, presumably times P of, but we're going to assume that the prior is constant. So we can just replace this with P of W given W map divided by the width of the prior. So this height over there, the posterior distribution, is going to be sitting at the posterior distribution of the data at the map value divided by the prior. So that kind of gives us roughly an estimate of the value of the peak, and then we've got the width of the peak, which is just going to be some quantity W posterior. So hopefully that kind of gives you a bit of an impression of where this comes from. Very simple. Okay, and here's kind of this. Here's kind of a picture describing it. And so now taking logs, we obtain that the log of the data is equal to the log of the, again, here we have, so it's going to be the log of the log posterior of the data given our best parameters, which will, for more complicated models, we'll do better. But now we have this expression, we have this term, which is the ratio of the width of the posterior over the width of the prior. So this approximation is illustrated in figure 3.12. So here is what's going on. The prior is this thing over here. It's got that width. So we have a whole range of values to pick from. But now that we've actually seen some data, then that's going to shrink, right? So here now it's going to shrink to smaller width of the posterior, and that's kind of what's coming up in this expression, and it's also showing up here. So after seeing the data, necessarily our width is going to become smaller, and that's what's going to be used in this expression for the probability of data given the model. This approximation is illustrated because the first term represents the fit to the data given by the most probable parameter values. And we saw that, and for a flat prior, this would correspond to the log likelihood. The second term penalizes the model according to its complexity. Because the width of the posterior is less than the width of the prior, because the prior essentially tells you which values are allowed in any without having seen anything, and you can only choose effectively you can only choose from among those. You're limited to those before you observe any data, and then once you observe the data, well, then you get a narrow subset of those prior values are going to be consistent with the data. So the width of the posterior is going to be less than the width of the prior. So because of that, this term is negative, and it increases in magnitude as the ratio gets smaller. Thus, if parameters are finely tuned to the data in the posterior distribution, then the penalty term is large. So I think that's kind of the key thing, right? So the idea is that if you have kind of a high order model, well then this kind of width posterior is going to be like super sharply focused over, on your best possible on the best possible model. And also, but there's going to be kind of a second effect that and we don't quite see it here because we just have a single parameter, but we'll also have that the width is, the overall size of the space that you fit is going to be larger. So there's going to be kind of two things. You're going to have this very thin relative width of the posterior, and then it's kind of large contribution to the prior. So if parameters are finely tuned to the data in the posterior distribution, then the penalty term is large. So here is just talking about the aspect of we have a single parameter. So if you're kind of finely tuned, well, this is going to become very small, and so you're going to get a penalty because of that. Now, for a model having a set of m parameters, we can make a similar approximation for each parameter in turn, assuming that all parameters have the same ratio of width posterior to prior. Then you get this exactly the same expression, but now this penalty is now multiplied m times. So he says, thus, in this very simple approximation, the size of the complexity penalty increases linearly with the number m of adaptive parameters in the model. Now, as we increase the complexity of the model, the first term will typically decrease because a more complex model is better able to fit the data, whereas the second term will increase due to the dependence on m. The second term will, so I'm not sure because I think this is going to be actually a negative number, right? So the contribution of this is as you increase the model parameters, your penalty is going to get larger. So this is going to be actually going to become it's going to decrease. It's going to become actually more and more negative. Whereas as your models become more complicated, this term should actually increase. So you're going to fit the data. You're going to fit the data better with your best parameter is going to fit the data better, but the penalty that you're going to get is going to get more negative. So you're going to be penalized more heavily. So I think I'm going to put a question mark because I think he means the other way around. He means that as we increase the complexity of the model, the first term will typically decrease. This should probably be increase because the more complex model is better able to fit data, where the second term will decrease, I think. Let me know what you think as well. The optimal model complexity as determined by the maximum evidence will be given by a trade-off between these two competing terms. Okay. We can gain further insight into Bayesian model comparison and understand how the marginal likelihood can favor models of intermediate complexity by considering figure 3.13. Yeah, this is another kind of one of these cartoon figures, which again I think is still useful to look at. Here the horizontal axis is a one-dimensional representation of the space of possible data sets, okay? So that each point on this axis corresponds to a specific data set. We now consider three models, M1 to M3, of successively increasing complexity. And now imagine running these models generatively to produce example data sets and then looking at the distribution of data sets that result. Okay? Any given model can generate a variety of different data sets since the parameters are governed by a prior probability distribution. For any choice of the parameters, there may be random noise on the target variables. Right? So even even our kind of simple linear model that we had could generate data that was coming from a sinusoid, right? Because you can imagine, well, it's a really noisy version of a line. To generate a particular data set from a specific model, we first choose the values of the parameters from their prior distribution, and then for these parameter values, we sample the data from P of D given W. So this is again going back to this notion, right? Effectively talking about this. So we're going to sample the parameters from the model, and then generate data from those parameters, and then essentially compare that data to what we actually see. Okay. A simple model, for example, based on a first-order polynomial, has little variability and so will generate data sets that are fairly similar to each other. Its distribution P of D is therefore confined to a relatively small region of the horizontal axis. So, the data sets that it assigns kind of high probability to, it can still, again, you can compute a probability for the sinusoidal data set, but it's going to give it a very low probability. So it's kind of its domain of high probability. It's going to be quite narrow. By contrast, a complex model such as a ninth order polynomial can generate a great variety of different data sets, including the one we have exactly, right? And so its distribution PFD is spread over a large region of the space of data sets. So this guy here. Because the distribution are normalized, so the integral over the data has to sum to 1, we see that the particular data set D naught can have the highest value of the evidence for the model of intermediate complexity, right? So you essentially want the complexity to be like just large enough that your data kind of fits into it. These super complex models, yeah, your data fits nicely inside, but because they're normalized, the probability they assign to your data set is going to be much lower, because there's so many more data sets that they can actually fit. Essentially, the simpler model cannot fit the data well, whereas the more complex model spreads its predictive probability over too broad a range of data sets, and so assigns relatively small probability to any one of them. So I think this is a very important statement and an explanation of model selection, about what's going on, why you want the balance between the two types of models. Implicit in the Bayesian model comparison framework is the assumption that the true distribution from which the data are generated is contained within the set of models under consideration. Provided this is so, we can show that the Bayesian model comparison will on average favor and we'll see that's important. To see this, consider two models in which the truth corresponds to M1. For a given finite data set, it's possible for the Bayes factor to be larger for the incorrect model, right? It's possible that, like, for example, on the, if we had the out of the ninth order polynomial, it's possible that on a particular data set, it really fits it fits the data very well. So it's possible that the more complex model will fit on a particular data set really well. But on average, the point is that on average, the correct model will actually win if you know what it is. So to see this, consider two models, M1 and M2, in which the truth corresponds to M1. For a given finite data set, it's possible for the Bayes factor to be larger for the incorrect model. However, if we average the Bayes factor over the distribution of data sets, then we obtain the expected Bayes factor in the form this. So notice what's happening here, right? So we're integrating over data. We're averaging, we're weighting data according to they're being generated from the true model. So we're weighting this Bayes factor according to the probability of data coming from the model that we know to be accurate. And we're just saying, well, what is this Bayes factor on average for any other model? And the point was that this can actually be, occasionally can be, I guess, less than 1, suggesting that the second model, the model that we know is false, can win for a particular data set. But if you actually average over all possible data sets, you'll notice what this is. This is actually the callback Leibler divergence between these two, and we know that it's always going to be greater than or equal to 0. So on average, this Bayes factor, if you average over the data sets, the Bayes factor for the correct model will actually be larger, so which will indicate that on average the correct model, if you have it, is the data is going to be more likely for the correct model on average over all data sets. So thus on average the Bayes factor will always favor the correct model. Again, not necessarily on any given data set, but on average. Okay. And I think this is a pretty cool expression, and stuff like this comes up all the time, just using the fact that the callback Leibler divergence is always positive. You can kind of prove lots of interesting things, and they often come with like a cool information theoretic insight, like this one, that on average, the correct model is going to win out. So just kind of keep an eye out for points like that. Okay. Yeah, I think now in the next little bit, he's going to talk about some of the caveats. So, okay, we have seen the Bayesian framework avoids the problem of overfitting and allows models to be compared on the basis of training data alone. However, a Bayesian approach, like any approach to pattern recognition, needs to make assumptions about the form of the model. Yes, for example, this comes up like, when you've got your prior, okay, so let's go back up here. So, when you're integrating over your parameter values, you have to often set, okay, well, what's the width of that parameter space, right? Is it going to be infinite? Well, often it can't be infinite, like unless you have some decay terms that you have to specify, right? You're gonna have to say, well, yeah, yes, the domain is the whole real line, but I have the width, I favor small values of the parameter. And again, so that's going to introduce a parameter itself. And we'll see. So you're gonna have to kind of make these assumptions. And if you don't, for example, if you use an improper prior, then things are going to blow up because, for example, this whole expression requires, it's like a key part of this is the fact that this prior distribution is normalized, and so more complicated models are going to have a smaller value of that prior for any given parameter value. If you have an unnormalized prior or you have an improper prior, well, that goes out the window, and all of a sudden, you're going to have your complicated models winning out, and things of that nature. So that's kind of what he's going to be touching on now. So we see that the model evidence can be sensitive to many aspects of the prior, such as the behavior and the tails. Indeed, the evidence is not defined if the prior is improper, as can be seen by noting that an improper prior has an arbitrary scaling factor, right? In other words, so that P of W, we just talked about it. The normalization, in other words, the normalization coefficient is not defined because the distribution cannot be normalized. If you consider a proper prior and then take a suitable limit in order to obtain an improper prior, for example, a Gaussian prior in which we take the limit of infinite variance, so we say, look, okay, all right, I want, I'll just make my Gaussian wider and wider, then the evidence will go to 0, as can be seen from, these figures, right? So, as this, as this width of the prior goes, gets smaller and smaller and smaller, your evidence is going to shrink. So, yeah, so the width of your prior is going to go to infinite. So this thing is going to go to 0. So it doesn't necessarily help you out there. It may, however, be possible to consider the evidence ratio between two models first and then take a limit. So there might be some ways around it. But again, he kind of concludes with saying that in practical application, it would be wise to keep aside an independent test set of data on which to evaluate the overall performance on the final system. So yeah, I think in practice, we all, for some of the reasons he touches on, like when you want to compute these integrals to compare the models, it's often you have to kind of make different sets of choices. Often the integrals can be a bit complicated. Often you have to pick your priors in a certain way, and so like in practice, people, including myself, we do end up using kind of cross validation, and kind of more kind of frequentist approaches. Kind of I guess everyone kind of understands them, and yeah, some of the assumptions sometimes I guess there's just less to. There can be kind of less to explain. They come with their own kind of assumptions that you have to kind of make sure are okay, and that they also mean that you are always training on a fraction of your data. But again, I think the importance of knowing about the Bayesian approach to model selection is that it kind of tells you what's actually kind of really happening. Well, I want to say on an abstract level. It's not really on an abstract level. It's actually it's the reason why complex models can kind of bring with themselves kind of their own kind of penalty, and you can kind of see where overfitting comes from, where you're not properly accounting for the complexity of your model. So your model fits your data well, perfect, but you're missing a second half that says, well, a model that complex can fit all sorts of data well. So in that, so it should kind of naturally be regularized. So I think it's just kind of important for giving you insight into kind of overfitting and regularization, and something to keep in mind, even if at the end of the day, we end up just using kind of test sets and validation sets, etc. Cool. So I think that was kind of a nice kind of high level discussion of model selection, because it's an important topic. It does come up all the time, so good to kind of get a big picture view of that. And the next time we're going to be essentially heading towards the end of the chapter. We're talking about I think one method which I haven't used myself, so we'll be learning it together, of I guess actually computing some of these these model selection values that we need, but having to make some approximations. So hopefully I'll see you then. And as usual, please just tell me, let me know how you found the lecture. If you've found some bits confusing, if you thought I explained something incorrectly, please let me know. Happy to fix that. Yeah, any comments are always welcome. So hopefully I'll see you next time when we talk about the evidence approximation. Bye for now.